Hello, everyone. I'm Everton de Oliveira from the Groundwater Project, and I'm very pleased to bring you two more authors of fine books that we've been producing. I have here with us today Kirk Nordstrom. Kirk is a hydrogeologist at the U.S. Geological Survey for the last 47 years. Wow. And I have also Pauline Smedley. And Pauline is a hydrogeologist at the British Geological Survey for a little less longer, of course. Not everybody can have the pleasure to work for so many years in such a nice institution like you guys do. So welcome, Kirk and Pauline. Please introduce yourselves. Tell a little bit about your careers and, introduce yourself for our future readers. Pauline first, if I have to pick.
Okay, sorry, Kirk. Obviously, I'm a relative newcomer to this business compared to Kirk, of course. I've worked for the British Geological Survey as a geochemist for the last 3 decades, but it pales into insignificance compared to Kirk. I started back in the day. My first boss with the British Geological Survey was the late, great Mike Edmonds, who introduced me to the topic of trace elements in groundwater and drinking water in relation to human health. And I've retained that interest ever since.
It's very good. You, Kirk, please.
Well, yes, I call myself a hydrogeochemist because I have a background in chemistry, geology, hydrology, and a little bit of microbiology. But I've always, ever since I was in undergraduate school, I've realized that the U.S. Geological Survey was a great institution that did some top-notch research in water chemistry and water quality and many other things as well. But it attracted my attention, and I was determined to get a job there, which was not easy, but I managed to do that and enjoyed a lot of that work, which has covered trace elements, major elements. It's covered uncontaminated waters and contaminated waters. A lot of my work has to do with acid mine drainage, and that's where I got heavily involved with trace elements and redox species. At the same time, I was fascinated with the development of geochemical codes that could do very complex calculations fairly easily, and participated a little bit in the development of those codes and have used them quite a bit in my work. Also, I've come to realize that not too many people have been involved in the actual analysis of the water, but that's something that I've not only done since I was a graduate student, but we have our own lab and we've developed it, and we have realized that's an integral part of everything we do. And it's a really important thing that not that many people do, because most people take a water sample, send it off to a lab, and they tend to trust the results, which most of the time you can do, but not always. And you have to know something about analytical chemistry to evaluate where the data you're working with can be interpreted in the way that you think.
Very good, very good. So before I jump into into your book, Fluoride, let's ask you, how did you get to the Groundwater Project?
I guess I should start, because I sort of encouraged Pauline to join me on this, because she and Mike had done such nice work on earlier reviews of the subject. But I was contacted by John Cherry, and he very much wanted me involved. And since I've known John a very long time, and I totally trust him, I like everything he's done. He's just an outstanding hydrogeologist. It was hard to say no to his invitation to work on this. That, combined with the fact that the subject of fluoride in natural waters is one that I've been interested in ever since I can remember. So it was an exciting opportunity that I gladly accepted.
Very good. Very good. So, Pauline, I understand that Kirk twisted your arm to
Eventually, yes. Yeah, no, fluoride has been very close to my heart for many years too. So it was, yeah, it was a pleasure to join in as well.
Very good, very good. So first of all, why fluoride? And what is the reader you're aiming at with your book? Pauline first now. Sorry, Kirk.
Oh, okay. Why fluoride? I'll do the first bit, Kirk. Okay, why fluoride? Fluoride doesn't occur in all drinking water, of course, but there are many parts of the world. Globally, it's an important problem. There are estimated to be over 200 million people globally drinking water, drinking water, groundwater, and there is principally a groundwater problem with excessive concentrations of fluoride above drinking water standards. And it's important to try and understand why they occur, where they occur, and to try to mitigate against the problem.
Fluoride it's an interesting element which is not necessarily always a part of routine water analysis for major constituents. During my search of the literature, I was surprised how many papers there were where I'd come up with some very nice groundwater analyses, but the fluoride was missing. And I was just appalled at that, of course. And I didn't tell Pauline about it because she would have been horrified at it. But it's sort of called a minor element. So it's not, generally speaking, a major element, major solute like sodium, potassium, calcium, magnesium, chloride, and so on. But it should be routinely analyzed whenever you're doing major solutes, not only because of its importance in drinking water and health, but because it makes a difference to the whole water chemistry and what its composition is, where it comes from, and so forth. So as mentioned, I've been interested in fluoride for a long time. I suppose it started with the fact that I was fascinated with minerals and crystals as a kid, and I started a mineral collection. And when you start collecting minerals, one of the first things you notice is that fluorite, the mineral fluoride, calcium fluoride, is a beautiful crystalline material that comes in every color of the rainbow and has different crystal forms. It's just an amazing thing. So that attracted me originally, and I have sort of grown up with wanting to know more and more about fluoride. And graduate school, I started doing a little research on it, and have not stopped. And the whole problem with fluoride in groundwater, it's most of it's naturally occurring. Even today, not that many people realize that it's not uncommon to find fluoride in concentrations too high in groundwater when you're developing groundwater supplies for a community. And hopefully this book will help people understand that it's not everywhere. It's not in all aquifers. Somebody once said to me, well, in most cases, fluoride is not too high in concentration. And I replied with, I don't know what most cases are because I'm not sure that anybody has the data to say something like that. Now, if somebody were to ask me, do you think that, just a guess, that most groundwaters have no more than about 1 milligram per liter fluoride, which is safe, or below, which is safe? I would say, well, probably if you put on some caveats. If you say the water, the wells are not deeper than about, I don't know, 50 meters, you restrict them to shallow groundwaters, then probably most of them have acceptable amounts of fluoride. But if you say 100 meters, then I'd say, no, it's probably the other way around. But it's because nobody's really done that sort of analysis, and the data would be hard to put together as well. It's a hard thing to say. the point is there is a lot of it out there, and you have to be careful. And it should always, when you're developing new groundwaters in an area, you should always test and get a fairly complete analysis.
Very good. Your book is very thorough. You have, like, you covered everything. That's a wonderful job. You had some research before, I'm pretty sure, because you have so many nice information put together in this book. I was well impressed about it. So how did you manage? Let's go to a more technical question first. What are the natural sources of fluoride in groundwater and how it behaves? Because that's very important when you're doing hydrogeology and have a feeling when you go to the field and try to understand.
You start, Kirk.
Oh, you're letting me.
Well, let's vary.
Well, the two most common minerals that fluoride is found in are fluorite, the mineral fluoride, calcium fluoride, and the mineral apatite, which commonly has some fluoride in the structure, and when it does, it's called fluorapatite. And their fluorite is more soluble than fluorapatite, but they're both soluble enough to contribute a fair amount of fluoride to the groundwater. But it depends upon do those minerals occur in the rocks? They're fairly common in a wide range of rocks, but not all rocks. Also, are they of a material that's reactive enough to dissolve substantially? And that depends mostly on grain size. If it's very fine grain material, then it's more soluble. And also it depends on a number of factors, like the rest of the water chemistry. If it's of the right type, if it's of a sodium bicarbonate type water, and a higher pH, it's much more likely to have higher fluoride in it. And that's one of the things we try to describe in our book is how groundwaters chemically evolve in order to reach this level of unacceptably high fluoride concentrations.
That's good. Pauline?
So high fluoride, these fluorine-bearing minerals tend to be concentrated in some specific rock types. So granites often contain high concentrations of these fluorine-bearing minerals, and silicic volcanic rocks as well, rhyolites and so on, and volcanic ashes that go along with them. So in areas of granite and volcanic rocks and volcanic ashes, there tend to commonly problems with fluoride in groundwater. But also in sedimentary rocks, particularly where there are phosphate minerals in there, phosphorites can have high concentrations of fluoride associated with them. But as Kirk says, it's not just the geology that is important in deriving these fluoride problem areas. It's the water chemistry that goes along with it, the two coupled together.
Yeah, good. Well, Kirk, just for those who don't know, you were mentioning that a shallower is less likely to have. So tell us a little bit about the evolution of fluoride then for that interpretation.
Well, first of all, shallow waters tend to have a low residence time. They wash through the sediments or the rock fairly quickly and don't have the opportunity to pick up as much fluoride or other trace elements as well. And so they're likely to be a little cleaner, more dilute, more drinking water acceptable. And whereas deeper waters, having a longer residence time, being in more contact with rocks and sediments, are going to pick up more constituents and are more likely to have high fluoride. In general, that tends to be true. But there are other factors as well. So we talk about the evolution of a groundwater in what we call recharge areas, where snow melt and rainfall infiltrate and go into the ground. Typically, you have what are called calcium bicarbonate waters, and these won't have much fluoride in them unless it's a highly mineralized area, which would be unusual.
Yeah.
But as they go down gradient through, let's say, a sedimentary aquifer, for example, they go through chemical changes like ion exchange, where the calcium comes out onto a clay mineral and sodium is bounced into the water. So there's a sodium calcium exchange that goes on. That gives you an evolution from a calcium bicarbonate water to sodium bicarbonate water. And along with that process, you tend to get some additional carbon in the water, sometimes from organic matter degrading. And all of this changes the water chemistry in a certain direction, usually to higher pH values, which tend to promote more rapid dissolution of fluoride-bearing minerals. And so the fluoride concentrations go up. So there's quite a few aquifers that are used for water supplies around the world that go through this evolution. And so knowing that, you would prefer to have your water supply sort of up gradient rather than down gradient. But if you have to have your water supply down gradient, then you want to check it and see if there's high fluoride in it or not, and be prepared to treat it if there is.
Yeah, good. Yeah, well, we have here in Brazil, in Guarani Aquifer, we have a very, very large region where the water is affected by fluoride. And in many places, people don't even, they just abandon the wells, which doesn't make sense because the water there, it's about 600 meters deep. It's an expensive well to start with, right? And it doesn't make much sense for us. But we're going to talk a little bit about treating the water later on in this talk. So the question is, are there relevant man-made sources of fluoride that we should consider? Pauline.
Yeah, there are some man-made sources. Of course, industrial effluents often contain high concentrations of fluoride. Results of phosphate processing or aluminium processing, for example, it could have an impact on wastewaters. And atmospheric emissions, coal-fired power stations, for instance, or brick-making works could release atmospheric emissions, and aluminium smelters could release fluoride into the atmosphere as well. But these are relatively local scale, relatively localized effects compared to the naturally occurring water rock interaction problems that fluoride occurs in groundwater much more globally, much more regionally than atmospheric emissions from human activities.
Yeah, well, but when we compare to, let's say, organic contaminants that's typical, they're quite big, the contamination from fluoride, because it doesn't stop, right? the fluoride is very soluble, it doesn't absorb on pretty much anything, right?
Yeah,
So
no, but natural water rock interaction, there can be many milligrams per liter, many tens of milligrams per liter in drinking water, and if you're exposed to that chronically for many years, then your long-term dose will be much higher from natural sources.
Yeah, that's true. Yeah. Well, I know because I've seen some man-made contaminations of fluoride, and they tend to have large plumes compared to let's say organics that can biodegrade in time. So fluoride goes a long way. That's the idea, right?
Yeah,
so,
but there are some plumes like these, but when you compare a plume in a localized area to most of the Atlantic coastal plain that has high fluoride going from somewhere in New England all the way down to Florida, that's a huge area.
Yes, that's a huge. Well, it's similar here in the Guarani Aquifer. Well, not as big as that one, but it's very big. Thousands of kilometers as well. That's pretty big.
And Peninsula India as well.
Oh, in India, yes, in India. Yes. By the way, you have many great case studies in your book. What are the main points that you could mention for those interested in looking for fluoride in their country's aquifer? Because I was very well impressed with the amount of information that you put in your book. So let's say if someone is interested in studying fluoride in their countries, what do you suggest?
Well, Everton, I'm glad you're impressed because it was a huge amount of work.
I could tell it. I could tell that for sure.
And it was a little bit of a problem because you want to mention and report on papers who have studied fluoride in the groundwater system, but if you put in some, if you feel like, well, you can't slight these other people who also did good studies in their country, and pretty soon the whole thing balloons up when you've got thousands of papers in the literature.
Yeah.
So yeah, this is one of the outcomes of having that big table that we have of the occurrences of high fluoride groundwater from around the world. There are a lot of places, and somebody in another country can see if there's any reports that we have in our table from their country. One other thing about that table that we decided to do sort of at the last minute is to have that table be a dynamic table. That is, to allow it to be updated, and people can look at it and say, oh, well, they missed something here. Okay, let us know, we'll put it in, and we'll keep the thing going. So it is more useful on the long-term basis for people.
Well, last minute, it took you long minutes to put that table in place there, right?
Yeah.
It's a very impressive table, for sure. I was
Kirk
checking.
did most of the work.
You have very good material there. Congrats, very good. Say, Pauline, sorry.
No, I was saying Kirk did most of the work on getting all those examples together. So yeah, big effort.
Yes, that was very, very good, very good. So fluoride is an important contaminant. Could you talk a little bit about the mitigation of excess fluoride in groundwater? As I mentioned previously, I've seen many wells, that are abandoned due to fluoride. What are your experience about that?
Well, because fluoride has been a problem that's been recognized for quite a long time, there have been several methods that have developed over the years to try and tackle it. And I guess the most common methods are coagulation, precipitation, adding some kind of aluminium salt or the salt to the water to precipitate out and take the fluoride with it. Or the other method, the common methods are adsorption and ion exchange techniques. So alum is one of the most common coagulation techniques. You add aluminium sulfate and they precipitate out a flock of aluminium hydroxide, which takes the fluoride with it. Or ion exchange methods could be anything from commercial ion exchange resins or activated alumina, activated carbon, that sort of thing, right down to local raw materials like local soils or clays, some clays, or iron oxides, aluminium oxides, or clay pots, or crushed bone, or bone char, or even rice husks. All sorts of different techniques have been tried at different scales and in different technologies, depending on the local circumstances. And even, in developed societies, reverse osmosis is also a technique that is commonly used, except that takes quite a lot of energy and is an expensive method, so isn't suitable for remote or developing country settings. And yeah, quite a wide range of different techniques have been applied with varying degrees of success, I'd say.
That's true. That's true. I've seen many. You're correct. You presented them on your book. That's quite good. So, Kirk, what would you say to a reader that starts working with fluoride? Why is this necessary? Let's talk about the problems with someone that drinks fluoride for a long time, for example, long exposure. Why should we study fluoride?
for human health reasons, clearly, but also it can affect livestock as well. So animals are affected by this that have the same bone structure that humans have. I mean, it's because it's such a large problem worldwide. You know, that's an important reason to study it. I was surprised many years ago when an estimate was made about how many people in India were exposed to high fluoride water, and it was on the order of 60 to 65 million people, and it's estimated to be a little bit higher than that now. Correct me if I'm wrong, Pauline, but it's something in that order. And we've heard a lot about people being affected by arsenic in groundwater, which is also a very serious problem. But it's come to my attention that there are more people affected by fluoride than arsenic. But the human health disorders, the problems that you have, the sickness that you have, is a little different, quite different, because the fluoride affects your teeth and your bones, whereas arsenic can attack any of the organs in your body. And then, of course, how big of a problem it is depends upon dosage, as we've been saying, and then people, you know, they as soon as it's recognized that there's too much fluoride or arsenic in their groundwater, they try to get people off of that, get it onto a decent water supply. But the big problem is there's a lot of places around the planet where there isn't any other water supply, at least not within convenient or economic means, and so then they're forced to treat it, and sometimes they don't have enough economic resources to treat the water as well, or treat it in enough capacity to help enough people. And I think we're going to see this as a growing problem, because we're extracting more and more groundwater all the time. In fact, the groundwater resource extraction seems to be exponentially increasing without an exponential increase in the treatment where it's needed. So
Yep.
this is just continuing to be a big problem.
By the way, India extracts 1/3 of all groundwater extracted in the world. It is a lot of groundwater. So
they have a huge area of their country that's just dry, and there's no water except groundwater. And a lot of groundwater has fluoride, and some of it has arsenic.
Arsenic, yes. That's so sad. Yeah, you're correct. You're correct. Okay, guys. I'd like you to, I'd like to talk about your book for a lot longer, but then we will leave the readers, you know, to check by themselves what is in your book, because it's a great work. Congratulations. Please, guys, thank you very much for showing up here today and talking about nice work. Please make your final statements. Again, Pauline first.
Final statements. I guess science has taught us a lot over the decades about the identification of the problem and locating it and understanding its causes. But I think the problem, as Kirk has already said, the problem is actually solving the problem, mitigating against the problem, particularly in these large areas of the world in semi-arid and arid conditions where groundwater is the only source available, and there is no alternative but to treat the water. So I guess for the generations of the future, it is to resolve this problem of mitigating, treating water to remove the fluoride. And these local solutions to treating the water with locally available materials are always prone to problems, sustainability problems in the long run, when the onus is on the owner to actually try and treat the water themselves. I think there needs to be more in terms of local testing in these areas that are not well tested, to try and identify where the worst problems are. And more distributed supplies of managed water, treated water, to all but the most remote areas. And perhaps trying to develop methods of managed aquifer recharge to increase the infiltration to try and see if that might mitigate the problem, or at least alleviate the problem. And then rainwater harvesting might be a last resort, but it might help at least part of the year for some communities at least. Yeah, but sadly we haven't resolved the problem of treating the drinking water yet.
Thank you very much. Very, very nice. Kirk.
Well, it took science a rather long time to be able to analyze fluoride in both rocks and water quantitatively. But now we can do it more or less routinely. We know a lot now about how certain groundwaters get high fluoride concentrations. And the whole science of hydrogeology has advanced quite a bit. What we need to do more now is to apply that information, apply that science to water management problems, to bring to the fore the fact that you can't make political decisions about water management without the science. And we can do that effectively if allowed to. We hope this book will go a ways in that direction, will contribute to the better understanding and use of our groundwater supplies.
I hope so too. I'll make a big effort here to get it translated into Portuguese as soon as possible. It's quite important for us here. And I'm pretty sure people will love to have this book available in other languages. So it will be, I'm pretty sure, in the very soon future. Congratulations for a very nice work that you put. I love your book. It's an important read for hydrogeologists, and I hope it'll be a success because you deserve it. All right, thank you very much. And you, if you're watching us, please consider making a donation for the Groundwater Project. It's a volunteer work. People are working for love, and that's an important move to keep us going ahead. Thank you very much. Bye, everybody.